The vector equation of a line. Now, you've studied equations of a line in grade 10, y equals mx plus b. We are going to do the same thing thinking about y equals mx plus b, but only use vectors. And the nice thing about doing this with vectors is then we can easily extend it to 3 dimensions, where with what you've done with y equals mx plus b, you've been limited to 2 dimensions. So when you have a line, and we're going to imagine this first in 2 dimensions, we've got the line that's going through A, R, and C. If you were figuring this out with y equals mx plus b, the b would be your y-intercept, which would be a specific point, and m would be your slope. What we do in vector equation of line is something similar, but instead of having a slope, we have a direction vector. And instead of having just the y-intercept, we can start with any point. So when we have an equation of a line, y equals mx plus b, you can plug in a whole bunch of different x values and get different y values, and all of those points would be on the line. With the vector equation of a line, it's the same idea. We want to find the position vector of any vector on the line. So what we do is we start with one vector. Here we have the position vector A. A is on the line. We also have the position vector C, or R. C. Yeah, let's do C. Hello. We have the position vector C. C is on the line. And going from A to C, we have a direction vector. So that red vector is the direction vector, and it would be, if you wanted to go from A to C, can you see that you could do that by doing negative A plus C? If I go negative along A and plus C, that would be the direction vector AC. Now, if I wanted to find another point on the line, so I pick a random point on the line R. There's my position vector R. I could get to R by starting at A and going in the direction of AC by some proportion. In this case, it looks like a little bit less than half. If I had to do my best guess, I might say maybe 3 or 4/10 of the way. Does that make sense? If I start at A and go 3/10 of the way to C, I would end up at R. And so our equation for R looks like this. I'll do it in purple. The vector R is equal to starting at the vector A and then going in the direction of AC, which we're going to call that vector B, going in the direction of B by some multiple that we don't know. And if we include all the multiples of t all the way along, we could get anywhere. If t is negative, you would go in this direction and get points backwards. If t was double, you would go double in the direction and hit another point. And if t is every single number, we would hit every point along that line, and that would make a line, which is the same thing as your table of values does for a regular line. Every time you plug in x, you get another y value. And every single one would plot another point on the line. But instead of plotting points, we're finding position vectors that end on that line. So we use B for the direction vector. And you can write negative A plus C if you like the visual, or just C minus A. And t is any scalar or any multiple that you have. So the vector equation of the line, once you have it, there are 2 other forms that you can write it in. One of them is called the parametric form. So if you look at the components in 2 dimensions, you'd have your x and y of your position vector. You've got your starting vector, which is vector A, so I'll call that A1 and A2. And then we have our direction vector has an x coordinate and a y coordinate, B1 and B2. The parametric form just looks at the components separately. So what are our x coordinates? Well, they're equal to A1 plus the scalar t times B1. And our y coordinate is A2 plus our scalar times B2. If you take your parametric equation, you could rearrange it to get t by itself. And if you do that in both equations, since t is the same number, you could then equate these fractions, and that's called the Cartesian form. Rearranging the Cartesian form in 2 dimensions will always end up giving you y equals mx plus b for the same line. So we'll see that example coming up. Find the vector equation of the line L passing through the point 2, 5 and parallel to 3i minus 4j. So we'll draw a picture just to have an idea of what's going on. Two, 5 is the position vector of a point on the line, and it's parallel to 3i minus 4j. 3i minus 4j would look like this. Go over 1, 2, 3, go down 1, 2, 3, 4. Does that make sense? We've got 1.2, 5, and if it's parallel to 3i, which is 3 in the x direction, negative 4j, which is 4 down, we would have this equation. So we know from our old style of math, we know that the slope of this line is negative 4 over 3, rise over run. Our vector equation of this purple line, all we need is a starting vector. Any one will do. And we need a direction vector. Well, our direction is going 3 to the right, 4 down. And so if we know the direction and we know any point, the vector equation line is really easy to write. In fact, it's probably easier to write quickly than y equals mx plus b. Because right now, I don't know what my y-intercept is. I can figure it out, but I can't see it right away. So there's our vector equation of a line. If we want to write the parametric form, that's looking at each of the components. So the x component is 2 plus 3t, and the y component is 5 minus 4t. If we want to find our Cartesian forms, remember we need to solve for t in our parametric forms. Can you see that the first equation, if I subtracted 2 on both sides and then divided by 3, would equal t? And our second equation, if you added 5 to both sides and divided by a negative 4, you would get t. So our Cartesian form just makes those equal, takes the t out of the picture. And what's fascinating about the Cartesian form is you could simplify this. So for example, if I multiplied both sides by 3 and multiplied both sides by negative 4, I would get negative 4x plus 8 equals 3y plus 15. If I move things around to get y by itself, I would have 3y is equal to negative 4x minus 7. And dividing everything by 3, I can rearrange it and find out, hey, that's y equals mx plus b. Was the slope of my line negative 4 over 3? Yes. And now I know my y-intercept happens to be negative 7/3. But I get that value by rearranging my Cartesian form. So the Cartesian form is connected to what we've done in the past with y equals mx plus b. But what's really nice about the vector form is you can start with any point as long as you have the point and the direction vector. So in a lot of ways, do you remember, go back one more. There we go. No, one more. There. Do you remember this equation of a line? It was called the point slope form. The point slope form said plug in the slope and plug in any point. And then almost always we had to rearrange it to get it into y equals mx plus b or a different form. But a vector equation of a line is probably most similar to your point slope form. Because in the point slope form, you needed the slope and a point. In a vector equation, you need any position vector and a direction. The direction is like your slope. The position vector is like any point. Find the vector equation of a line L passing through the point 2, 5 and perpendicular to 3, 1. So first of all, we've got a point 2, 5. And we need something perpendicular to 3, 1. So this, whatever goes in here, has to be perpendicular to 3, 1. Well, if we think about this as slopes, if you went 3 over and 1 up, could you tell that that slope of that line is going to be 1/3? How do we find something perpendicular? Negative reciprocal. And so this vector in here is going to have to be 1, 3. And we're going to need to change one of these values to negative. And it doesn't matter which one. If you did negative 1 and 3 or 1 and negative 3, both of those would be the same. Once again, it asks for the parametric. That's your x coordinates. And your y coordinates. And the Cartesian. For the Cartesian, we solve for t. In the first one, you would get x minus 2 divided by negative 1 would be t. In the second one, you would get y minus 5 divided by 3. Again, the Cartesian one, we could rearrange to find out y equals mx plus b if we wanted to, but we do not need to. So these first couple examples have given us a position vector to start with and the direction. This third example gives us 2 position vectors on our graph. So what do we know? Again, you can kind of draw a graph of this. We've got the point 1, 4, that's on our line, and we've got the point 5, 8. So from 1, 4 to 5, 8 is going to be our direction vector. How do we find our direction vector? Well, if I call this point is point A and this point is point B, I don't like my my direction vector would be, I would have to go from A back to my origin. That would be negative A. And then I would have to go from my origin to B. This is why the lettering is a little bit bad here, because I wanted to say B equals, and then I have to use A and B again, so that was going to be a little problematic. But negative A plus B, what does that look like? And a lot of students just start doing B minus A just because it's easier to put in and subtract, and our direction vector is going to be 4, 4. Now, when I write the equation of the line, I would pick any point. So let's say I went around and someone had chosen 1, 4 plus t, and then they put their direction vector. And then somebody else had said, well, you're wrong. This is what I have. I have 5, 8 instead. Plus 4, 4. Who's right?
I am.
There we go. Record, Mr. Tacky is never right. But if two people wrote these down, they're both the same. Both would be fine. You just need any starting point, so the fact that one person chose 1, 4 and the other person chose 5, 8, they would both be fine. And then someone else goes, well, I like 1, 4 because it was written first, but I don't like writing so many 4s, so I'm just going to write 1, 1. They are right as well, because 1, 1 is parallel to 4, 4. And all we need is a direction and say we need to walk in this direction to get to another point on this line, and any multiple of any parallel one will work. Right? So if you really, really, really want to make my life difficult on the exam, right? And you have, if the direction vector is 3, 2, and you decide, oh, I'm going to multiply both of them by 73 because it's parallel, and Mr. JR will have to check, right? You could be mean like that to me. Of course, I might make a mistake in checking and just mark you wrong. Anyways, no. Any one of those answers would be right. The key is we need any point, and we need any a direction vector, and it doesn't matter which one you have as long as it's parallel to it. It's kind of like slope. Does it make sense that the slope of this one is 4 over 4? We're going 4 in the x direction, 4 in the y direction. Slope is rise over run, right? And this one's slope is 1 over 1. Can you see that they're the same? It's just fractions have been simplified. And now we can go to 3 dimensions. The idea is the same. In 3 dimensions, we have a point to start with, and we need a direction vector. So our direction vector here I can use B, will be from P to Q. And P to Q is negative P plus Q, or Q minus P. If I take Q, 2, 0, negative 4, and I subtract P, 1, 5, 3, I get 1, negative 5, negative 7. There's my direction vector. So my equation of my line take any point you want, multiply our direction vector by a scalar t. And we've just taken the same concept, and now we're dealing in 3 dimensions. And we don't do this with our math before. Like this has a slope, but it's like rise over run over, what do you call the, now it's on a, like if you have it up, down, but that's sort of like rise, then you have like rise 1 over run over rise, it gets complicated if you try to describe it with 3 dimensions, and so vectors work really, really nice. So the question is, does the point -1, 3, 5 lie on the line? If it does, there's a t-value that makes this true. We put in the point for r. We had our original equation line, which I'm going to just go back here and steal for a second. 1, 5, 3. 1, 5, 3. Was it 1, -5, -7? Yes? And so there would have to be a t-value that makes this true. I'll slide this over this way. Slide this over. Oh, here, oh, fancy. Cool. Now we can look at the parametric equations for each of these. The first one says that -1 would have to equal 1 plus t. Can you see that you could solve for that in equation 1? That's not a t. T would have to be -2. And if I plug in the second value, I would get 3 would have to equal 5 minus 5t. If you solve for that, you get t equals 2/5. We can already say it's not on the line. We don't even have to do the third one. We could do the third one if we wanted to. The third parametric equation, if you solved for that one, you would get t equals -2/7. If it was on the line, there exists a t-value that makes it work. In our case, it doesn't work. And so we can say that it is not on the line. But if we got t equals 2, t equals 2, t equals 2 for all three, we could say that it works. All right, so what about 3, -5, 5? What do you think? If we write it out, we put 3, -5, 5. Man, I cannot remember. Did I get them right? No, 1, 5, 3. So close. So let's find out. The first equation would tell me 3 would equal 1 plus t. Second equation would be -5 would equal 5 minus 5t. And the third one would say 5 is equal to 3 minus 7t. Solve for the first one. T is equal to 2. Solve for the second one. T is equal to 2. Solve for the third one. T is equal to negative 2/7. No! Not on the line. I just committed a major teaching offense. What do teachers always do when they're showing you examples? One that doesn't work. And then if I asked you to put money on whether the next one would work, you would all say, yes, it's going to work. Right? But no, it came close. It started to look like it was going to work because t equaled 2 for the first two. And if we would have got t equals 2 for the third one, we would have said, yes, that point is on the line. But it didn't. So it's not on the line again. If I really wanted to make a teaching offense, I would have another 10 examples that all didn't work. But that would be a little bit redundant. So we find that we use the Cartesian form of the equation. I mean, not the Cartesian, the parametric form of the equation quite a bit to solve things. When we look at individual components here, we could solve for t and find out, does it work or does it not work? So what happens is sometimes we get equations in odd forms. Here they've got it all as one vector. Could you see that you could break up this vector? Sort of like they've got the parametric equations in one vector. So 3 and 5 would be a point, and then plus t, and the t is multiplied by 2 there, and negative 5 there. So if we get a weird form, can we rearrange things or think about it to write it in a form that we do understand? We want a unit vector in the same direction as L. First of all, let's look back at our line. What's the direction of this line? We look at our direction vector to find the direction. The direction of the line was to negative 5. Do you remember what a unit vector was? It's been a while. Unit vector in the same direction, well, it would be a vector with a length of 1. What's the length of this one? How did I do that? The length of that one's the square root of 29. Right? When we're figuring out a length, it's just a squared plus b squared, square root of that. So that length is square root of 29. The unit vector then, we would need to divide this vector by 1 over the square root of 29 to make it a length of 1. So if this has a length of square root of 29, when I multiply by 1 over the square root of 29, I get a length of 1. Part C says find the Cartesian form of the line. Again, to find the Cartesian, first we need to find the parametric. So we look at our x-coordinates. Our x-coordinate was 3 plus 2t. Our y-coordinate was 5 minus 5t. The Cartesian form is when you get t by itself for both of them. and make them equal. Two lines L and M have messed up equations. That's not what it says, but that's what they look like. They're really kind of crazy. Can you see that whatever's in front of the I is sort of the parametric equation for x? Whatever's in front of the j is the parametric equation for y, and whatever's in front of the k is like your parametric equation for z. I can rewrite equation L. I know it's going to have the point 5, 3, and 0 plus s, and it's going to have negative 4, 1, and 2. And I can rewrite the equation M I know it has the point negative 3, 7, and 6. And negative 4, negative 1, and there's no t's in the last one, so 0. Find a position vector of their common point. Okay? We are going to almost all the time we want to solve something, we're going to use the parametric equations. So from my blue equation, I have x is equal to 5 minus 4s. Y is equal to 3 plus s. And z is equal to 2s. From my green equation, I have x is equal to negative 3 minus 4t. Y is equal to 7 minus t. And z is equal to 6. When you have your parametric equations, since you have two equations for x, can you see that I can use substitution and say 5 minus 4s has to equal negative 3 minus 4t. If they have a point in common, the x values would be the same. And so 5 minus 4s would have to equal negative 3 minus 4t. And similarly, 3 plus s would have to equal 7 minus t. And finally, 2s would equal 6. And we create a system of equations. We have 3 equations, and there's 2 things we don't want, that we don't know. Can you see that there's one of the things is really easy to solve for? 2s equals 6. What's s? S has to be 3. And if we know that s is 3, we could use either equation. Let's say I take the second equation, and then I say 3 plus 3 equals 7 minus t. Can you see that t has to be 1? And so we can say that there's a point in common when s is 3 and t is 1. Let's go back up to our equations. What happens when I plug s equals 3? 5 minus 12, negative 7. 3 plus 3, 6. 0 plus 6, 6. What happens when I plug t is 1 into this equation. Negative 3 plus negative 4, negative 7. 7 minus 1, 6. 6 plus 0, 6. You can write a statement in the end. Common point is negative 7, 6, 6. So now we have two lines in 3 dimensions. Imagine one this way, one this way. And we know that they intersect at the point negative 7, 6, 6. So if I draw a picture of what we know so far for this next question, I got one line here, another line here, and that point is negative 7, 6, 6. The next question is, what's the angle between them? Whew. Well, how have we figured out angles so far with vectors? We could use either the cross product or the dot product, but we've talked about how the dot product is better because cos of theta can tell us whether it's positive or negative, whether the angle is in quadrant 1 or quadrant 2. But in order to find the angle between them, we're going to need a green vector and a blue vector. And the green vector and the blue vector, you have to use the direction vectors of the lines. Because somewhere is, oh, the origin. I don't know where it is. I just picked a random spot. Somewhere we have the origin. And so if you use the point that's on the line, that's just going to give a vector from the origin to that point. But if you want the angle between these two lines, you need both of their direction vectors. And then we can use the formula that cos theta is the dot product divided by the lengths of each vector. So if I go back to my 2 equations of the lines, I had my blue equation had a direction vector of negative 4, 1, 2. So I'm going to write, that's that direction vector. My green line, it had a direction vector of negative 4, negative 1, 0. Whoa, I'm going the wrong way. Negative 4, negative 1, 0. So cos of theta equals, remember the dot product is multiplying components and adding them up. So negative 4 times negative 4 is 16 minus 1 plus 0 is 15. Then the length of u, 16 plus 1 plus 4, 21. The length of v, 16 plus 1 plus 0, 17. And we can go to our calculator and do cos inverse of 15 over the square root of 21 times 17. 37.5 degrees. And you could have your answer in radians or degrees, but this is a very typical exam question that I like to ask. Can you find the angle between two equations of a line? First of all, we have to make sure that those equations intersect, because sometimes you have two lines that never cross, then you can't find an angle between them. But in this case, since they do intersect, we can find that equation.